picture this. Your application just went viral. I mean, maybe a massive pop star just announced a world tour on your ticketing platform, or, a celebrity just tweeted a link to your e-commerce site.
The dream scenario.
Right, the dream. But suddenly your traffic just absolutely explodes. You go from a very comfortable, maybe 300 requests per second to a staggering 3,000 requests per second, almost instantly.
Yeah, which is terrifying.
Exactly. So does your system gracefully expand to handle that tsunami, or does it just entirely collapse under the pressure?
It's the ultimate nightmare scenario for any site reliability engineer, but it's also the ultimate test.
Yeah.
I mean, we like to think of our cloud architecture as this endlessly elastic resource.
Like magic.
Right, like magic. But the reality is that elasticity requires incredibly precise engineering. If you're just relying on default settings, your system collapses. It's really that simple.
Which is exactly why we are tearing down the 3-layer stack of Kubernetes autoscaling today in this deep dive. We're looking at the horizontal pod autoscaler, the vertical pod autoscaler, and node-level scaling.
Specifically comparing the traditional cluster autoscaler to its modern replacement, Karpenter.
Yes. So for you, the listener, whether you are prepping for a major launch, dealing with boasty workloads, or just, trying to optimize your cloud bills so you aren't paying for idle servers, the goal today is to stop guessing.
Stop guessing, yes.
We are going to decode how to combine these tools so your cluster scales efficiently without melting your budget. Okay, let's unpack this. Before we can even talk about scaling a system automatically, what actually happens at the ground level if we just throw a container into a Kubernetes cluster without telling the system anything about what that application needs?
Oh, man. You are basically setting a ticking time bomb.
A time bomb,
Right.
really?
Oh, absolutely. You can't scale a system if Kubernetes doesn't actually know what your applications need to survive. And that brings us to the fundamental baseline of, all autoscaling: resource requests and resource limits.
Right, okay.
A request is the guaranteed minimum amount of a resource like CPU or memory that the cluster reserves specifically for a container. And a limit is the absolute maximum amount that container is ever allowed to use.
Okay, so the request is the guarantee and the limit is the ceiling.
Exactly.
But if my container suddenly experiences a surge in traffic and hits that ceiling, does Kubernetes just, shut it down to protect the rest of the cluster?
Well, it depends entirely on which resource you max out.
Yeah.
Because CPU and memory behave in completely different ways. Memory is what we call a non-compressible resource.
Meaning you can't fake it.
Right. You can't magically squeeze 2 gigabytes of data into 1 gigabyte of RAM. It just doesn't work. So if a pod exceeds its memory limit, the system has no choice but to intervene with an ohm kill.
An out-of-memory kill.
Yeah. The operating system literally terminates the process. Just kills it dead.
Ouch. So the application just crashes and burns. What about CPU then?
CPU is much more forgiving
Wait.
because it's compressible. It basically represents computing processing time. So if a pod asks for too much CPU, it doesn't die.
Oh, good.
Well, instead, it suffers from CPU throttling. The system actively restricts its processing time. So, for example, based on your limits, the cluster might say, your pod is only allowed to use 30 milliseconds of CPU time in every 100 millisecond window.
Wait, so for the other 70 milliseconds of that window, the application is just frozen?
Frozen solid.
Wow.
Yeah, the container stays alive, but performance degrades massively. Your users experience terrible latency, timeouts, and just general sluggishness, even though the pod hasn't technically crashed.
Okay, so if we know the difference between these limits and guarantees, how does this actually connect to the autoscaler itself?
Right, the autoscaler.
Yeah, like if I'm using the horizontal pod autoscaler, HPA, it looks at utilization to decide when to add more pods. But if we never gave it a baseline request, how does it know what 80% utilization even looks like?
It doesn't.
That feels like asking an accountant to calculate your tax bracket, but refusing to tell them your salary.
That is the perfect analogy. And yet, missing that step is the #1 cause of autoscaling failures in production.
Wait, really? The #1 cause?
By far. This is the golden rule of HPA. It calculates utilization strictly as a percentage of the request. So if you don't set explicit resource requests on every single container, HPA literally cannot compute the math.
It's just sitting there.
It just sits there paralyzed while your application gets absolutely crushed by traffic.
So it's just driving blindfolded.
Completely blindfolded. In the postmortems we analyzed, so many catastrophic outages start right here. Teams focus heavily on setting limits to protect the cluster, but they neglect the requests. Yeah, if you want Kubernetes to make intelligent decisions about adding more pods, you have to give it the baseline guarantees to work with.
Okay, so we've hired the accountant, we've handed over our salary data, the baseline is set. Now we can introduce the two main actors at the pod level. HPA, which adds more pods, and VPA, the vertical pod autoscaler, which makes individual pods bigger.
Right.
But here's where it gets really interesting, because our sources highlight a pretty dramatic twist. If left unsupervised, these two tools will actually destroy your workload.
They absolutely will.
Right.
It's a classic case of good intentions going horribly wrong. And to understand the mechanism behind that destruction, we really have to look at how their control loops operate.
Okay.
So HPA is designed to be fast. It operates on a roughly 15-second control loop that looks at your target utilization, say 50% CPU, and if your current usage spikes to 80%, HPA immediately does the math and provisions more pod replicas.
Just to spread out that load.
Exactly. It's built for horizontal scale, which makes it incredibly effective for stateless web apps.
And I'm assuming VPA operates on a totally different timeline.
A completely different timeline and a totally different philosophy. The vertical pod autoscaler is slow and analytical. It looks at historical usage data over minutes or even hours to figure out the optimal CPU and memory requests for individual pods.
So it's playing the long game.
Right. It's generally best for stateful applications or long-running batch workloads where adding more replicas just doesn't make sense.
Yeah.
And crucially, because Kubernetes pod specifications are immutable, meaning they can't be changed on the fly if VPA is running in auto mode, it actually has to kill and restart a pod to apply those new, larger or smaller resource requests.
Oh, wow. That sounds like a recipe for disaster if they cross paths. Putting them both on the same metric sounds like a bad sci-fi movie where, like, two AI systems meant to save the ship end up fighting each other over the steering wheel.
That's exactly what happens.
Let's walk through that exact feedback loop. Say that pop star announces the tour, traffic spikes, CPU hits 80%. HPA does its job, right? It immediately adds more replicas to spread the load.
It does. And because that incoming traffic is now divided among, say, 10 pods instead of 2, the average CPU utilization per pod drops significantly.
But then VPA wakes up from its slow cycle.
Yep.
It looks at the historical data over the last few minutes, sees that the CPU utilization has plummeted, and decides, hey, these pods are way too big for this workload. So VPA actually shrinks the resource requests.
Which is where the death loop begins. VPA restarts the pods with smaller CPU requests. Because the requests are now smaller, that exact same volume of incoming traffic suddenly causes the utilization percentage to spike back up to 80 or 90%.
Which instantly wakes HPA back up.
You got it.
HPA sees the new spike, panics, and adds even more pods. The load spreads out, CPU drops again, and VPA shrinks the pods again. It's a vicious cycle.
Completely vicious. You end up with oscillating replica counts, unnecessary pod evictions, dropped connections, and just total chaos.
Wow.
This is why the official Kubernetes documentation contains explicit warnings against using HPA and VPA on the same resource metric for the same workload. If HPA is scaling based on CPU, VPA should never be managing CPU requests in auto mode. If you let them fight over the same steering wheel, your application will lose every single time.
So how do we establish peace? If they fundamentally conflict, how do expert cloud architects actually use them together in the real world without causing a total meltdown? Because both tools offer incredible value.
They do, yeah.
We need specific design patterns to safely combine them.
Well, our sources highlight two primary patterns for production. The safest and most common approach is pattern 1, running VPA in off mode alongside an active HPA.
Off mode.
Yeah. In this setup, VPA acts purely as an observer. It monitors your workloads and generates mathematical recommendations for right-sizing your CPU and memory, but it doesn't have the permission to actually touch the running pods.
Oh, I see. So VPA is essentially acting as an advisory board.
Exactly. Human engineers take those VPA recommendations, manually update the YAML configuration files to adjust the requests, and meanwhile, HPA is the only system actively handling the live horizontal scaling during traffic spikes.
It gives you the data-driven insights of VPA without the operational risk of a conflict.
Right. But for teams that want full automation, there is pattern 2. In this setup, you isolate their responsibilities. You configure HPA to scale strictly based on CPU utilization, and you configure VPA to exclusively manage memory requests.
I love the off-mode pattern, but pattern 2 feels a bit like patting your head and rubbing your stomach at the same time.
It's definitely advanced.
I get the logic. I mean, you let VPA control memory sizing because you can't horizontally scale your way out of a memory leak or an OM kill. And HPA handles the replica counts based purely on CPU demand. But what happens if VPA decides to restart a pod to resize its memory right when the pop star tweets, and HPA is desperately trying to handle a massive traffic spike? Couldn't VPA accidentally take down the very pods HPA needs?
That is a great point. If we connect this to the bigger picture, you've just identified exactly why advanced autoscaling requires pod disruption budgets, or PDBs.
Okay, PDBs.
You never deploy pattern 2 without a PDB. A pod disruption budget is a cluster-level safety net. It communicates directly with the Kubernetes scheduler. You can configure it to declare that, for example, at least 75% of your pods must remain running and available at all times, no matter what.
Oh, that's brilliant. So even if VPA decides a pod desperately needs more memory and wants to evict it, the scheduler looks at the PDB, sees that evicting that pod would drop the available fleet below 75%, and just blocks the eviction.
Exactly. The scheduler vetoes VPA. It acts as a built-in failsafe, ensuring your application always maintains a minimum threshold of availability even while automated systems are trying to optimize it in the background.
Okay, so we've sorted out the pod layer. We stopped the AI systems from fighting. HPA successfully asks the cluster for 40 new pods to handle our Popstars ticket sale. But pods are just software. They're logical constructs. They need physical hardware, actual servers or nodes to run on. What happens when your cluster physically runs out of room for those 40 new pods?
We have to move down to the third layer of the stack, right? Node provisioning.
This is where the rubber meets the road. Traditionally, this layer was managed by the cluster autoscaler, or CA.
Right.
Cluster autoscaler sits in the background and watches the cluster for pods that are trapped in a pending state. A pod goes into pending status when the scheduler looks at all the existing nodes and realizes none of them have enough spare CPU or memory to host it.
It's basically waiting in line.
Right. So when CA sees these pending pods, it triggers an API call to your cloud provider to provision a brand new node.
But our sources point out a fatal flaw with the traditional cluster autoscaler.
It's the timeline, right?
The timeline is the absolute Achilles heel. It generally takes 2 to 5 minutes for cluster autoscaler to get a pod running.
Wait, 5 minutes?
Yeah, up to 5 minutes.
In internet time, a 5-minute wait during a viral traffic spike means dropped requests, failed checkouts, and a timeline full of angry tweets. Why did we ever accept 5 minutes as a normal reaction time for cloud infrastructure?
Because for a long time, we were constrained by the underlying cloud architecture. I mean, cluster autoscaler doesn't just magically conjure a server. It has to negotiate with rigid autoscaling groups, or ASGs, provided by the cloud vendor.
Okay.
It updates the desired capacity of the ASG. Then it has to wait for the cloud provider's internal polling cycles to notice the change, then wait for a new virtual machine to boot, wait for the operating system to load, and finally wait for the kubelet, the Kubernetes agent running on that new node to phone home and register itself with the cluster.
That is a highly bureaucratic process.
Very bureaucratic. But this is where Karpenter fundamentally changes the equation.
Yes, I've seen Karpenter mentioned everywhere in these architectural guides, especially for AWS environments. How is it actually shaving 4 minutes off that boot time? What's the mechanism?
Well, Karpenter completely bypasses those slow, rigid autoscaling groups. It essentially cuts out the middleman. When Karpenter sees pending pods, it evaluates their specific resource requirements and makes a direct call to the cloud provider's bare metal compute API.
Direct to the metal.
Exactly. It provisions the right-sized instance directly. Because it isn't waiting on the ASG's polling loops, it can bring a new node online and schedule a pod in just 10 to 30 seconds.
10 to 30 seconds instead of 5 minutes? That is a staggering improvement.
It's the difference between surviving a viral spike and going offline entirely. It turns node scaling from a sluggish, delayed reaction into a rapid dynamic response.
Yeah.
And what's really fascinating here is that Karpenter works in reverse, too.
Oh, really?
Yeah. During periods of low demand, it actively consolidates workloads. It shuffles pods around to pack them tightly onto fewer nodes, terminating the underutilized instances to instantly cut your compute costs.
So what does this all mean for our architecture? We have the full 3-layer stack built. HPA handles the immediate demand for more replicas, VPA optimizes the sizing without fighting, and Karpenter provides the physical nodes in seconds rather than minutes.
The Holy Trinity.
Right. Now let's put it to the ultimate test, that massive, instantaneous 10 a.m. burst in traffic when the tickets go on sale. How do we configure the dials on these tools so we aren't reacting too late? Because even 10 seconds might be too slow for a massive API hit.
That's very true. The first rule for extreme bursts is to stop relying solely on CPU metrics.
Stop relying on CPU.
Yeah, CPU is a lagging indicator. By the time the CPU on your pods hits your 80% threshold, your system is already overwhelmed and your users are already experiencing latency. If you know a massive spike is coming, you have to shift to custom metrics, like queue depth or requests per second RPS.
But how does Kubernetes even know what my application's requests per second are? HPA looks at CPU and memory out of the box. How do we feed it custom data?
You bridge the gap using a tool like the Prometheus adapter. Prometheus monitors your external application metrics, like the traffic hitting your load balancer or the depth of your messaging queue, and translates that data into custom metrics that the internal Kubernetes API can actually understand.
Oh, I see. And using RPS is incredibly powerful because it's predictable math.
Yeah,
You aren't guessing based on how hot the processor is running.
exactly.
If you know that one pod can comfortably handle 1,000 requests per second, and Prometheus tells HPA that 10,000 requests per second are hitting the load balancer, HPA instantly knows it needs exactly 10 pods.
Precisely. It
Yeah.
removes the guesswork entirely.
Hmm.
Now, the next dial you have to tune is your target utilization strategy.
Yeah.
It sounds counterintuitive, but your target depends heavily on the type of workload.
Okay, how so?
If you are running a background batch workload like processing video files overnight, you want to set aggressive targets, maybe
Yeah.
85% utilization. You want to pack those nodes tightly to save money because a little latency just doesn't matter there. But for a latency-sensitive API like our ticketing checkout, you actually want conservative targets like 50%.
Wait, targeting 50% utilization means you are intentionally running your pods at half capacity. Isn't that wasting money?
It's buying insurance. Running at 50% instantly doubles your capacity headroom. If that viral spike hits, your existing pods have a massive buffer to absorb the initial wave of traffic, while Karpenter's taking those 10 to 30 seconds to provision new nodes in the background.
Oh, that makes total sense.
Yeah, if you run your APIs at 85%, a sudden 20% spike instantly throttles your CPU and brings down the service before Karpenter even wakes up.
You're buying time for the hardware to arrive.
Exactly.
And our sources also dive into the concept of asymmetrical HPA behavior. You want to tune HPA to scale up incredibly fast, but scale down incredibly slowly.
That asymmetry is vital for stability. You can configure HPA with a 0-second stabilization window for scaling up, meaning the absolute second Prometheus detects a spike, HPA fires off a request for more pods.
Zero hesitation.
0. But for scaling down, you might set a 5-minute stabilization window. This prevents the system from flapping prematurely, killing off pods because traffic dipped for a few seconds, only to immediately need them again when the next wave hits.
So, looking at our ticketing platform scenario, the smartest cloud architects don't just sit back and wait for the auto-scaler to play catch-up. If you know the Popstars tickets go on sale exactly at 10 a.m., you pre-scale.
Absolutely.
At 9:55 a.m., you manually bump the minimum replica count in your deployment. You force Karpenter to spin up the nodes early so the hardware is warm and ready the second the clock strikes 10.
This raises an important question, though. You mentioned earlier that predictable math relies on knowing that one pod handles exactly 1,000 RPS.
Right?
How do you actually know that? You don't guess. You only discover that number if you relentlessly load test your application to find its absolute breaking point. You have to simulate traffic in a staging environment until your 95th percentile latency crosses your service level agreement, say 50 milliseconds.
So you find the breaking point first.
Yes. That exact breaking point is what informs
Yeah.
every single math equation in your HPA configuration.
You have to measure. You can't guess. The math only works if the baseline is real. So, to wrap up our deep dive today, we've explored the incredible synergy of this 3-layer stack.
We really have.
HPA handles the real-time, demand-driven replicas, scaling out mathematically based on custom metrics. VPA ensures those pods are sized efficiently over time, configured safely so it doesn't fight HPA for control of the steering wheel. And Karpenter bypasses the old, slow auto-scaling groups to provide physical hardware directly from the cloud provider in seconds rather than minutes.
It's a beautiful system when it's tuned right.
It really is. For you listening right now, I challenge you to open up your own Kubernetes clusters today. Check your deployments. Ensure you have those baseline resource requests set so you aren't flying blind, and verify that you aren't committing the cardinal sin of running HPO and VPA on the exact same CPU metric.
And I'll leave you with a final provocative thought about where this technology is heading next. We've spent this entire time talking about scaling up to handle massive bursts. But there is a modern concept called KEDA Kubernetes event-driven autoscaling.
Okay, Kita.
KEDA allows you to scale your workloads based on external events, like a message arriving at a Kafka queue, all the way down to zero.
Wait, down to zero, as in the application just doesn't exist.
Down to zero. No pods running at all, no compute costs.
Wow.
What does it mean for the future of your cloud architecture when your infrastructure literally disappears overnight when no one is looking, saving you entirely on compute, only to instantly rebuild itself the precise second a single customer event occurs?
That is wild to think about. Your entire architecture just vanishing and reappearing on demand. It brings us right back to that pop star tour dropping, only this time, instead of expanding from 300 to 3,000 requests per second, you're expanding from 0 to 3,000. Now that is a true magic trick.